Okay, so now, thank you for coming. We have here a great talk. We are honored to have Peter Kennedy with us. He will talk about recent advances in frequency synthesis. Professor Peter Kennedy received the bachelor degree in electronics from National University of Ireland and the master and PhD degrees from University of California, Berkeley, and a doctoral engineer degree from the National University of Ireland. He has a vast number of publications in several areas like nonlinear circuits, oscillators, CASS, neural networks, mixed signal testing, phase lock loops. And he was appointed a fellow for his contribution to the study of neural networks and nonlinear dynamics. I will not continue with all these awards. Just I would like to point out that he was founding director of Ireland's Microelectronics Industry Design Association and the Microelectronics Circuit Center in Ireland. So, and is the president of the Royal Irish Academy from 2017 to 2020. Professor Kennedy, is really a pleasure to have you here, really, indeed. So I will pass the words to you now.
Okay, thank you, Sandro, and thank you, Ricardo, in the background for this invitation. It's clear that this is an extremely dynamic chapter. You attract a huge audience, as I see, from around the world, and it's a great pleasure for me to be able to present to this group. As Sandro has said, my background is nonlinear circuits. Now, I started in chaos theory, and many people think chaos theory is completely useless. When I returned to Ireland from America, not knowing what to do next in my career, I went to the industry and thought maybe I could do something with industry here. They asked me, what do you do? I told them I did chaos theory, and they said, well, can you do anything that's useful to us? So about 20 years ago, I started to look at PLLs, and I got more and more interested because PLLs are full of interesting nonlinear problems. And in particular, the area of frequency synthesis, there's a vast number of very, very interesting problems. So I'm not a circuit designer, I'm a circuit theorist. And coming from a nonlinear background, one of the things that we do is we generally can't get explicit solutions for nonlinear systems. So we're very interested in qualitative behavior. When we see a pattern, we want to know what's causing that pattern, and are there fundamental properties of systems that cause that type of behavior. So in my talk, you'll see that I focus on qualitative things a lot. Okay, so let's get started. I'm going to talk about recent advances in frequency synthesis. I will talk mainly about a particular type of fractional-N frequency synthesizer and some specific phenomena that are important both from a practical point of view, but especially from a research point of view. So frequency synthesizers are everywhere, and I'll show you some of the uses. I'll talk about the things that we're specifically interested in, which is phase noise and spurs. Then in terms of frequency synthesizers, there are two different classes, integer N and fractional N. I'll explain the difference between those. I'll focus then on the thing that's of particular interest to me and my research team, which is nonlinearity-induced noise and spurs. I'll then talk about some of the mitigation strategies that others and ourselves have studied over the years, and some recent architectures. So these will be from circuit designers, showing how some of these ideas are used in practice. At the end, I'll give some thoughts on where I think it all might be going next. So frequency synthesizers, this is from the datasheet of Analog Devices, one of their latest microwave frequency synthesizers with a VCO. So there's a VCO in this, which is the core of the PLL. And then there's a block over here, which is the digital delta sigma modulator. And that's the piece that's of most interest to us. But frequency synthesizers, they're used fundamentally in radio applications for channelization. So they'll use as local oscillators to set channel frequencies. They're also used, you can drive them dynamically to set to do frequency modulation. In digital circuits, they're used for clocking, they're used for wireline transmission, they're used in data converters, for high precision data converters. You need to have a very precise clock. In satellite navigation systems, they're increasingly being used in radar, and there's lots of interesting problems coming up in the radar domain. And then in power systems with renewable energy, again, there are a lot of interesting problems coming up. So what is frequency synthesis? Well, at its core, one wants to produce a sine wave. So in the frequency domain, the sine wave is just a pure tone. It's all the energy is concentrated at a single frequency. In the time domain, we have a nice clean sine wave. Now, in practice, you don't have a nice clean sine wave. There's some noise on it, so this is indicated here. In the frequency domain, that noise appears as what's called a noise skirt, a phase noise skirt. So instead of being a pure tone, there's some noise around it. Now, other representations, I'll be using this representation from Mike Perrott, showing there's the phase noise in the frequency domain. So that's the signal you want. There's the phase noise unwanted. And in the time domain, you'll see that the signal kind of moves around a bit. Now, these two things, clearly this is the same thing, but people working in the RF area tend to work in the frequency domain and talk about phase noise, whereas people working in digital circuits are typically more interested in the time domain and talk about jitter. But the two things are essentially the same. So when we talk about phase noise, the generic term is phase noise, but there are two slightly different versions. One is just a noise-like signal, and that noise-like signal is just described in units of dBc per hertz. So how many decibels relative to the carrier in 1 hertz of bandwidth. So that's kind of a power density level. Spurs, on the other hand, or spurious tones, these are periodic components, unwanted or spurious periodic components, and these are indicated in dBc. So how far down are they from the carrier? So if you look at an overall phase plot, you'll see you can have it in dBc, or if you look at the total noise, phase noise, you can characterize it in, so this would be dBc per hertz, and then there's an area here of hertz. So the total power in here is going to be dBc associated with that skirt. So they're the units that we'll see. Here's an example from Skyworks. This is the measured phase noise plot of a particular frequency synthesizer, and you see the characteristic pieces. So there's an envelope here, and then there's some unwanted periodic components, and you can characterize how much power is in the periodic components. That's typically given in dBc, and then how much power is under here. So you'll have dBc per hertz, and then you integrate that over a particular area, and again you'll get a total dBc. The number will be presented for the digital guys in jitter. So there's periodic jitter associated with a spur, periodic jitter associated with another spur, and then there's a total jitter, which is the total integrated noise under here plus the spurs. So these things are presented in different ways, but you can always go back and forth between them. Now, why are we interested in the phase noise and spurs? Well, if you think of the frequency, well, when the synthesizer is used as a local oscillator, generally all you want to do is you want to take a baseband signal and multiply it by a pure sine wave to move it to another frequency band. If you multiply it by a pure sine wave, then you simply move it in frequency. But if when multiplying it by the sine wave, you also have this noise, phase noise skirt associated with it, then the signal you want is moved to the frequency you want, but the phase noise skirt appears as well. So if you imagine a signal to noise ratio of the original signal, after you've moved it, you have signal to more noise. So the signal to noise ratio is reduced. But also you have these additional components that are in other frequency bands and might be interfering with other users, for example, in a communications application. So that's why communications people are very concerned about the phase noise. They're also concerned about spurious tones. So if you have another tone, well, you'll make another copy of this somewhere else, and that could interfere with another user. In the clocking domain, or increasingly in data converters, if you have, say, an ideal sine wave and you want to digitize it, if you digitize it with a pure clock, a pure sine wave clock, then you'll get out the nice digitized sine wave. But if your clock is instead noisy, then the signal after you've digitized it is noisy as well, and so you've reduced the signal to noise ratio. So the keeping jitter to a minimum, or equivalently keeping phase noise to a minimum, is essential in these applications. So let's look at the basic architecture. I've drawn kind of a generic architecture here for what's called the integer N frequency synthesizer. At its core, there's a controlled oscillator that's producing the output. You can imagine this is the sine wave that we want to produce. And it's the frequency of that output is controlled by this control signal here. So by varying the control signal, you can vary the control of the output, the frequency of the output. Now, in order to lock that output to a particular frequency, you take that output, divide the frequency down, typically through a counter or something, you divide that frequency down, and this is the signal we call div. That divided down signal is compared with a reference, very accurate reference coming from a crystal oscillator, for example. The difference between those two is minimized in this control loop, negative feedback. The key operation here is measuring the distance between, say, two edges or zero crossings. You measure the distance between those. You try to drive it to a minimum. You have a filter to clean the signal so that a DC signal ideally is applied to the controlled oscillator, and that signal is kept constant. So let's imagine you want to produce an output of 1 gigahertz and you have a reference of 100 megahertz. Well, then if you take the gigahertz, divide it down by 10, you have 100 megahertz here, 100 megahertz here, lock them together, and your output is locked to 1 gigahertz. So basically, the output frequency is given by a constant, an integer, times the reference frequency. The reference can be extremely precise, and so you can get an output that's extremely precise multiple of that reference. And this is what's called integer N frequency synthesizer, because you have an integer N here in the feedback path. Now, this allows you basically to produce output frequencies that are integer multiples of the reference. So in this case, if we had a reference of 100 megahertz, then we could produce outputs of 100 megahertz, 200 megahertz, 300 megahertz, and so on. But we couldn't produce any frequencies in between. Now, there's a lovely paper, and anybody interested in this field, I suggest you read Mike Barat's paper from 2002. It's a beautiful paper where he does a model. He shows how to model the synthesizer. It's for a charge pump PLL, but the basic idea is the same. Within the physical circuit, you have a number of different blocks. So the phase frequency detector here, which is the time measurement block, is going to have some physical noise associated with it. The reference clock will have some jitter or phase noise associated with that. The charge pump, there'll be some physical noise associated with the transistors and that. There'll be some physical noise in the loop filter, some physical noise in the divider. So these components are marked in red here. The oscillator will be trying to produce a pure sine wave, and the noise skirt associated with the oscillator rolls off at minus 20 dB per decade. So that's what's indicated here in blue. So in this model, you can lump together the red components here, which are the physical noise components associated with the elements in the PLL. And then there's the blue piece here, which is associated with the noise in the VCO. Interestingly, there's also a periodic tone. Now, where the periodic tone comes from is that when you do the time difference measurement, typically this signal will be a square wave from the crystal oscillator, and the divided down signal will also be a square wave. So you're comparing edges of a square wave, but you're comparing it once per tick of the reference cycle. And that leads to a feed through here, a periodic signal feeding through here, which ideally is filtered by the loop filter. It's attenuated by the loop filter, but there's always some feed through here, which gives an unwanted modulation of the VCO. And that's what's called reference feed through, and it produces an unwanted tone at the output called the reference spur. Now, a model of this, a simplified model of this, you can take the components associated with the physical noise, and you can take the component associated with the VCO's noise and lump them together. So the VCO noise, you can think of it being injected here. All the other physical noise components, you can lump them all together and think of them being injected at that point. You can then work out what's the transfer function from those 2 points. So what's the transfer function from here to the output? What's the transfer function from here to the output? And you see that these components, the red components, are low pass filtered by the loop when they appear at the output. The blue ones are high pass filtered. Okay, so the VCO is rolling off at minus 20 dB per decade. It's high pass filtered, so it's fine. Out here, nothing changes. But in here, you can kill this piece, right? So you can kill this piece here. The physical noise of the components is low pass filtered. So it means that beyond the bandwidth of the loop, you can kill that component. And basically, the roll off here is determined by the filtering properties of the loop. So again, from Perrot, you can see pictures like this, which is, this is the physical noise, and the physical noise, you can attenuate it here. This is the noise from the VCO, and you can fix it here. So basically, there are 2 areas here. And if you're a circuit designer designing a VCO, what you try to do is to push this line down as far as you can. So the VCO designer pushes this line down as far as they can to minimize the phase noise. The PLL designer, or the synthesizer designer, working with the other components, tries to push this level down as far as they can. So if you've pushed this level down as far as you can, and you've pushed this level down as far as you can, then you can't do any better. And so the objective for the designer is minimize this level, choose the bandwidth so that you get the minimum phase noise overall. And that's the basic design strategy. So in that sense, the integer n synthesizer represents a performance limit. You can't do better than that. If you've done the best you can pushing this down, can't do any better. If you've done the best you can pushing this down, can't do any better. So if you have succeeded in designing a beautiful integer n frequency synthesizer, and you can use it in whatever application you want, then do that. Okay, so the best you can do is integer n. Try to use integer n if you can. However, in many cases, and it's becoming increasingly difficult to find cases where you can use just an integer n, because as we said, the synthesizer, if you had a 100 megahertz reference and you want to produce a gigahertz, then you can multiply it by a constant. You can multiply it by an integer 10. But if you want to produce 1.1 gigahertz, you can't do that. And therefore, the fractional-N synthesizer is used, or the fractional-N architecture. And so if you want to produce 1.1 gigahertz from that reference, you just want to make a number here that is, say, 1 over 10. So 10 plus 1 over 10 will allow me to do what I need. You can make that 1 over 10 with 2 integers. So you can have integers everywhere in your design. This is called the integer piece. This is called the fractional piece. Now, you have a block then, which is a divider controller. And the objective of the divider controller is you give it frac and mod, and you produce an output which, when added to int, gives you an average value here that's equal to frac over mod. Okay, so you get an average output that's frac over mod. Now remember that the divider controller can only, or the frequency divider can only divide by integers. So what you have to do is play with the value of n, dither it, move it around, so that on average it's dividing by int plus frac over mod. Okay. Here's another picture from Mike Perrott. This invention actually is very old, from Riley. This is the patent from 1990. Here's an example, thanks to Mike Perrott again. Let's say you want to divide by 4 1/4, okay? So you have a reference signal, okay? And you want to produce an output that is 4 1/4 times that. So here's the output that's 4 1/4 times the input. And the way you achieve that is in the feedback path, you divide by 4, 4, 4, 5, 4, 4, 4, 5, so that on average, you're dividing by 4 1/4. So you count, you can see it here, you count 4 cycles, count 4 cycles, count 4 cycles, then count 5, count 4, 4, 4, 5, 4, 4, 4, 5, and so on. Now, when you look at the ref and div signals and look at the distance between the edges of those, which is what we have to measure in the time difference circuit, that distance grows and then it resets and then it grows and then it resets. And you get this periodic signal, a sawtooth-like waveform, introduced into the system at this point. And you see that if you introduce a sawtooth waveform at this point, well, that will give you an unwanted modulation on the VCO and will produce spurs. And this is a fundamental problem with the architecture. Now, when the input is constant and if you have a simple periodic pattern like that, then clearly you get this periodic behavior and you get nasty, really bad spurs. So you can mix it up. Instead of dividing by 4, 4, 4, 5 in a simple way, you could divide by 3s and 4s and 6s and 2s and whatever, and randomize them in such a way that the average is always 4 1/4, and shape the spectrum so that the component of noise coming from this process is high pass shaped. So theoretically, you can high pass shape the noise, the quantization noise that's introduced by this process according to the black line. In practice, if you don't, if you have a constant input, you might get a whole bunch of tones rather than this smooth curve. But ways have been developed, including LSB dithering and other techniques, that allow you to guarantee that the randomization coming from the divider controller is sufficient that the signal spectrum of the signal coming from the divider controller looks very close to shaped white noise. So a lot of effort was put into that. That problem is pretty much solved now. You can have a divider controller that produces, that introduces quantization noise that's very much like simply shaped white noise, and that problem is solved. So going back to the synthesizer then, we had the components in the synthesizer due to the red ones here due to the physical components. We have the blue piece due to the VCO. And now there's an additional source of noise that ultimately ends up as phase noise, additional noise introduced into the loop. And this is the green piece here, the shaped quantization noise from the divider controller. So this piece is introduced here, and we indicate that in green. Now, it turns out that we said that this one is low pass filtered, this one is high pass filtered. The noise coming from the divider controller, quantization noise from the divider controller, is first integrated and then low pass filtered. Okay. So what happens is that shaped quantization noise that was looking like this is low pass filtered and flattened in that way. So what does it mean? It means that if you have done things right, then you can take the noise that's introduced by the divider controller and hide it under the spectrum of essentially the integer n synthesizer. So you can still have the phase noise performance of the integer n synthesizer with the added flexibility of being able to choose lots of frequencies that are more closely spaced than FRF. And if you, in principle, have done things right, that additional component from the divider controller is hidden here and you don't see it. So that's the dream of what the fractional-N frequency synthesizer can do. And in that sense, the integer n represents the performance limit for a fractional-N synthesizer. So a fractional-N synthesizer, by definition, is always going to be worse in terms of its performance than integer n. And our goal should always be to try to make it approach as closely as possible the integer n. Okay, so this is what you're supposed to see. This component is hidden below the integer n profile. In practice, you see something like this. There are additional components, these spurious tones. And where do they come from? Well, initially, there was lots of thought that they came from the divider controller, or they came from coupling in the package, or they came from the power supply, or they came from wherever. But this paper in 2003 from Steyert's group, they just did a circuit simulation. In fact, it was a MATLAB level simulation. And two things happened. You can show in simulation, MATLAB or circuit simulation, without any coupling or any strange electromagnetic effects, substrate coupling, anything like that. You see a higher noise floor. You predicted a noise floor that's down here. The noise floor is higher, and you see spurious tones. So the question is, where are they coming from? And as I said, from my background in nonlinear circuits, when I see something and I see it happening everywhere, then you say, well, there must be something fundamental going on here. So these are the kinds of things you see from all kinds of architectures in the frequency synthesizer circuit space. The companies that sell these claim they're better or worse than their competitors based on this kind of performance. You see them in all digital PLLs, you see them in sampling PLLs, you see them in charge pump PLLs, you see them in all kinds of frac-N synthesizers. And you notice that the patterns are very similar. So whatever you see, the patterns are very similar. So what's going on here? Why are these patterns similar? And why do they happen in every architecture? And the reason is fundamentally that they're in the architecture. So where are they in the architecture? Now, if you look at the blocks, there's a limited number of blocks. So where could they be? We said that the divider controller, the output of the divider controller could, if the input is kept constant, it could have periodic tones. Okay? But I also said that techniques have been invented to make sure that the output of this looks as close to shaped white noise as possible. So it's not coming from here. Okay, so we can be pretty sure that it's not coming from here. Okay, not coming from here. The loop filter is typically made with linear components. It's not coming from here. The controlled oscillator hopefully is staying at roughly the same frequency. So there shouldn't be too much going on here. It's probably not from here. The frequency divider, a lot of work has been done on frequency dividers. And so we can be pretty sure it's not coming from here either. So there's only one block remaining, and that's the time difference measurement block. So that additional noise and those spurs somehow are coming from the time difference block. Now you can show this very easily. If you take the signal that's introduced by the divider controller, it's a very nice, clean shaped noise-like signal. If you measure it with a measuring device that has a linear transfer characteristic, then the signal that comes out has the same nice shaped spectrum as you would expect. However, if you measure it with a device that has a nonlinear transfer characteristic, then two things happen. One, the noise floor is elevated and 2 tones appear, spurious tones. So the fundamental question is, well, where do the tones appear? How large are they? And how high is the noise? And basically my work for the past 10 years has all been in uh, where do these appear? How large are they? And how high is the noise? The signal coming from the divider controller, once you randomize it sufficiently, it isn't a sawtooth anymore, but it still has a kind of sawtooth-like behavior. It's like a very noisy sawtooth. You can partition any nonlinearity into the linear piece and the residual nonlinear piece. And if you do that, you see that an original noise signal, when passed through this nonlinearity, ends up with a higher noise floor and spurs. And in fact, the higher noise floor and spurs can be completely attributed to the residual nonlinearity. So there's something going on here. And basically what it is an interaction between a signal of this type and a residual nonlinearity. And that's the fundamental mechanism. So if the issue is I have the signal from the divider controller interacting with the nonlinearity, then how do I get rid of the problem? Well, it's the standard problem of how do you remove these nonlinear effects? We're trying to deal with a nonlinear characteristic, memoryless, just to make it easy. We could linearize the nonlinear elements, and I'll show you some techniques to do that. We could minimize the dynamic range. So if instead of traveling over the entire characteristic and seeing a nonlinearity, you just move over a small portion, it'll be like small signal and it'll be more linear. The other thing that's very interesting in what we're looking at the moment is modifying the statistics of the signal. So the signal that we actually apply, could we play with the statistics of that such that when it interacts with the nonlinearity, it is doesn't produce such bad noise and spurs. So the idea of linearizing the nonlinear elements, one of the simplest things to do in the case of the charge pump is a charge pump typically has some regions that are very linear and others that are not so, based on what's happening with the transistors. If you're at a crossover point or you're close to the top of the range for the current sources. So what you can do is apply a bias to the charge pump so that you can avoid some of the worse regions. And that way you can linearize it and you can make things better. You can also do things like correcting the nonlinearity. If you know what the nonlinearity is, you can do some correction afterwards. Or what's a little bit more difficult, you can do some correction in time so that you minimize the signal before it hits the time measurement block. So there's a number of techniques around that. The other thing you can do is to minimize the dynamic range. We said that if you apply a nonlinear signal to this, if you apply a signal to this nonlinearity, there's going to be distortion. But if you always stay at the same point as you do in the integer case, the edges are always in alignment, and so there's no nonlinearity. So if somehow you could reduce the swing of the input signal, so the difference between ref and div, you could make it look more like the integer n case. Now, this can be done with different techniques. So you can use a multi-phase clock and take the clock edges to make the difference smaller. You can have a fractional feedback divider. And a thing that's very popular at the moment and has great promise is using a digital to time converter in the feedback path or the reference path to move edges, to bring them closer into alignment. The last method is the one where we're doing work at the moment, and there's a lot of research in this area now, is to modify the statistics of the signal that's produced by the divider controller. The classic divider controller is a MASH, digital delta sigma modulator, but Galton's team introduced a thing called the successive requantizer that is provably immune to spurs. We developed a variant of that called the probability mass redistributor, and Choi and his colleagues in Korea developed two new techniques, TIPM and PDS, which are related. So here's the classic MASH. It's a noise, multi-stage noise shaping architecture. It's a finite state machine. Therefore, if you give it a constant input, you will get a periodic output. And therefore, you have to dither it to make sure that it doesn't give you spurs naturally. So by dithering it, you can make it the output look like shaped white noise. Very low hardware implementation cost, therefore it's very popular. We proved recently that if you have an nth order MASH, it's immune to L minus first order polynomial distortion. Any of you who use the Texas Instruments frequency synthesizer, you know that you can turn it up to fourth order MASH divider controller. And one of the benefits of that, of going up to fourth order, is that you get immunity in principle to third order distortion. The successive requantizer comes from Galton's team. It is very different from the classic digital delta sigma modulator. It's a cascade of quantization blocks. Each quantization block has a sequence generator. A random signal is applied. So each of these has a random number generator associated with it. A random signal is applied in each block, and that random signal is applied in such a way that you get an even output, and therefore when you divide by 2, so throwing away the LSB, it's a perfect quantization. This architecture is immune to polynomial nonlinearities of a certain order, and it can be optimized. The downside of it is that if you have a 24-bit signal as mod in your frac over mod in your fraction, you need 24 of these stages, and they're very large, power hungry, and area consuming. If you look at the implementation of that, so this is a charge pump, the original charge pump PLL with the successive requantizer. Successive requantizer is in here in the divider controller. There's a linearization block as well. The raw synthesizer has a phase noise profile like, sorry, not a phase noise profile. This is essentially like the filter profile. So this is the size of the spurs that you see at different offsets from the carrier. The spurs are minus 45 dBc in the raw synthesizer. If you then turn on the linearization, so you linearize it, you can get down to minus 55. If you then turn on the modification of the statistics via the successive requantizer, you get down to minus 70 dBc. So this record was set back in 2007 and stood for best part of 12 years. In 2019, we did a variant called the MASH probability mass redistributor. We looked at how you could change the statistics, the probability distribution of the output of the MASH in order to make the system less prone to the production of spurs. With that, going from the raw structure to linearizing and then applying the PMR, we could do second order or third order PMR, we could get the worst case spur down to minus 72. So these architectures, the Galton's work in 2008 was a spur at minus 70. The best anyone has been able to do is minus 72. When you normalize to the center frequency, well, then the performance here improves. So just watch these two numbers as we go along. This is the best absolute number, and this is going to be normalized. I've just normalized everything to 1 gigahertz for comparison. Here's another architecture, and this is with a sampling PLL. So this is, again, there's a VCO here, there's a GMC filter here. This is the sampling phase detector, so that's our time measurement block. There is a DTC here, and that's being used to bring the edges of ref and div into alignment in order to minimize the range of the nonlinearity over which you're swinging. This architecture was able to produce minus 64 dBc in 2019. Here's another variant from Mercandelli. So this is Levantino's group in 2020. And again, a DTC is used to bring the edges into alignment. There's a sampling phase detector again. This one, again, we're at minus 63 dBc. This is work from 2021. A DTC, again, used to bring edges into alignment, and a sampling phase detector. Now down at minus 72. Okay, so this architecture, which is with a sampling PLL and using the technique of minimizing the distance between edges with DTCs, has brought the raw spur performance to minus 72 and the normalized performance to minus 86. So this is extremely impressive. The modifying the statistics, this is a technique. This one is very interesting. It's an all-digital PLL where there's a ring DCO. Now, normally the oscillator in a synthesizer is an LC oscillator because of its great noise performance. This is a ring DCO, which is a lower inherent phase noise performance of the DCO. TDC doing the time measurement block, the edges brought into alignment using DTCs, and they're driven by this block called TIPM, which is actually modifying the statistics of the output of a MASH divider controller in order to bring to improve the performance when it interacts with the nonlinearity. They, worst case fractional spurs, the raw performance is minus 47. Turning on the TIPM, they go down to minus 58. This is a bang-bang PLL. So there's a bang-bang PLL, main bang-bang PLL here. Edges brought into alignment and the DTC linearized. This is again from Levantino's team. Minus 61 is the best that they could do. Choi's group again did another version with linearizing, minimizing, and modifying. So all three techniques used together, this time with the ring DCO, and go from minus 47 about to minus 63. Now, what's very interesting about what Choi has been doing is that if you look at the jitter, equivalently phase noise performance, and the worst case fractional spurs, over the years, the worst case fractional spurs have been getting better and better. This is our paper from 2019. This is Choi, but it's with a ring-based oscillator. So all the best performance has been with LC oscillators. This is with a ring-based oscillator, and they've brought the performance way down here, which is extremely impressive. Okay, so these are some of the all-digital PLL architectures. That's the Bang Bang from Levantino's group, and these are the two from Choi. The raw numbers aren't as good as the charge pump yet. These raw numbers aren't as good as the charge pump yet, but it'll get there probably. So just to compare all of the architectures I've shown, as I said, the raw numbers for the digital PLL, so this is a Bang Bang PLL and an all-digital PLL, the raw spur numbers still aren't the best, but the normalized numbers are extremely impressive. Okay, so what's the deal with this modifying statistics? Well, if you look at that signal that I showed you, the signal that's coming from the divider controller, the signal from the divider controller has a sawtooth-like character, but essentially the signal at any instant in time is sitting on one of these traces. So there's a number of traces here, and the signal is basically jumping out about between these traces. Okay. Now, if you look at, and that's periodic, if you look at those periods and flatten them all into one, then you get something like this. So there's a number of traces, and as you go forward in time, the signal just jumps about these traces. You can look at the distribution of that signal over the traces, and that's the probability distribution of the signal in time as it jumps around over these traces. Okay. Now, so there's the signal in time, jumping randomly amongst these traces with a probability distribution that's like this. The residual nonlinearity, let's imagine the residual nonlinearity is like this. Well, a sample that's applied here is going to be mapped to something over here, okay? So each of these traces here gets mapped through the nonlinearity to a piece here, okay? So the blue one here gets mapped to that, the green one gets mapped to that, the orange one gets mapped to that, and so on, okay? And then the signal lies on these traces with a certain probability. So you can map the probabilities as well. And here's an example at the output. You can say at this time, the signal is on that trace with a certain probability. It's on that trace with a certain probability. It's on that trace with a certain probability. It's on this trace with a certain probability. Okay. And if you work out then, well, where is it? Take the weighted sum of those positions, you find that it should be here. So this magenta curve is what we call the periodic nonlinearity noise. And it gives you a representation of where the signal is after it goes through the nonlinearity. If the periodic nonlinearity noise has high amplitude, then you get a large spur. The position of the spur is determined by the period of the periodic nonlinearity noise. And in particular, if you could drive the periodic nonlinearity noise to zero, there would be no spur. Okay? So here's the case of a MASH working with nonlinearities of different orders. This is a fourth order MASH applied to, sorry, it's a third order nonlinearity, and it's a frequency synthesizer with a third order nonlinearity and divider controllers, which are mashes of different orders. So when you apply a second order mash, you end up getting spurs. When you apply a third order mash, you end up getting spurs. But if you apply a fourth order mash, we prove that in the case of the fourth order mash, the periodic nonlinearity noise is constant, it's zero, and therefore you get no spurs. So the periodic nonlinearity noise in the case of the MASH 1-1 is this large signal, therefore you get large spurs. Smaller in the case of the MASH 1-1-1, and in the case of the MASH 1-1-1-1, the fourth order MASH, there's nothing. Okay? So that's the same idea if you read the papers by Choi about TIPM or a thing they call PDS. It's basically the same idea. The signals, when they pass through the nonlinearity, end up being distorted. If you change the statistics so that the samples are distributed over these, if they're distributed over these traces in such a way that you can maintain a constant PNN, then you don't see any spurs. So, in conclusion, in terms of the frac-N PLL, if you're designing a frequency synthesizer, the performance limit can be achieved by an integer n synthesizer. Therefore, if you have the opportunity to do integer n, do integer n. Minimizing the dynamic range of the time difference measurement block always helps because it takes a frac-N synthesizer closer to the integer n. Linearizing the nonlinearity always helps because it takes you closer to integer n. What matters, we believe, is the residual nonlinearity. After you've taken everything else out, what's left? And I think there's probably a connection to the integral nonlinearity, the INL of ADCs and DACs. When you've done everything and you've cleaned it up as best you can, and you're just left with the smallest residual nonlinearity you have, modifying the statistics then allows you to minimize the effects of that residual nonlinearity. So if you really want to get a frac-N synthesizer performing as well as an integer n, you need to minimize, linearize, and I'm suggesting modifying the statistics will give you the last little push. So that's it. The work I've described, the pieces that we did were done by my PhD students, who all have very nice jobs in industry these days. The chips that we developed have been done in collaboration with Analog Devices, and we're very grateful to them, because without their support, we wouldn't have been able to demonstrate silicon results. And that's it. Work funded by Science Foundation Ireland and the Microelectronics Circuit Centre of Ireland. If you want to get in touch with me, that's my email address, and a bunch of references at the end here for those who wish to see them. So that's it. Thank you for your attention.
Thank you very much. Thank you very much for for this great talk. Well, I don't see a lot of questions here at the moment, right? But I really enjoyed and this a concept of studying the nonlinearity to avoid and to reduce the disperses is really really interesting. I got intrigued in the last moment when you said that the there is probably a relation to the ADC and NL with that, right? So it means that we probably will go through a study on the ADC architectures to verify where this nonlinearity is coming, and use this techniques for that as well.
Okay, so from we've been trying to figure out. Okay, I mentioned there were three problems. So there's the problem of what's the additional noise? How does the noise floor move with the nonlinearity? Okay, and that relationship is non-trivial. We thought it was fairly straightforward. And is it related simply to the INL? We're not sure, and that's an area for investigation. The next one is the position of the tone. Okay, so the position of the tone, sorry, the amplitude of the tone. Once we find the amplitudes of the spurs, the amplitudes of the spurs are somehow connected to what's the shape of the nonlinearity and what's the relationship to the profile or the statistics. So we're not clear about how that works either. And could you characterize it with a simple number? That's the goal would be, if you could say, I can predict it based on the INL of the residual nonlinearity, that would be great. Can we do that? I don't know. We're going to try to see if it's possible and try to make that connection.
So it means we're gonna see some Peter Kennedy works on ADCs.
No, taking some concepts from ADCs. You mentioned that I did mixed signal. Yeah. One of the first things I did when I talked to industry was to develop a technique for characterizing, or in a production setting, measuring the INL of DACs in a very efficient manner. So that's it started because the INL of resistive ladder DACs has a fractal structure, and so that was the connection between the industry guys who wanted something practical done and the CASS guy who knew about fractals. Yeah. So it would be interesting to do something else in that connection between the. Where's the link to the INL? Is there one? And can we find something useful there?
Oh, great. Okay, so I don't see questions here, so I have another one. But let's move back to the PLLs, right? So my question is actually regarding the receiver application where I
Hmm.
work, basically, right? So suppose we are developing something like IoT or maybe satellite IoT, right? So which of the topology we are maybe not so much worried about the spurs,
Hmm.
maybe not so much, right? But in terms of performance, for instance, can you suggest one of the architectures that you would look in terms of this?
So
Uh,
in terms historically, in terms of RF performance, and even today, the best RF performance is coming from charge pump PLLs with LCVCOs. Okay, so
mhm,
that's if you just want the best performance, that's what you do. If you want to do something that's in an SoC or is working at very low voltages or something else, there are other requirements, and there's a need to go into a highly digital architecture, then there are lots of things to explore. So, um, I mean, the lesson for me is if you can get away with an integer n architecture, that's always better because you're going to have fewer problems.
mhm,
If you can't do integer n, then um, there's a lot to do. The the sampling PLLs are turning out to be very, very interesting, and I think
mhm,
there's a lot to be discovered there. They sampling PLLs were studied a lot back in the 1970s, and then
mhm.
they disappeared for a long time because of implementation difficulties. But now they're back, and the nonlinear problems haven't gone away; they're still there. But the architectures are producing great numbers.
Okay, great, great. Yeah, yeah. Let's look into the sampling PLS. Now we have one question from Benching. So since the bang bang phase detector gives the linear phase detection, is it possible to achieve smaller than minus 100 dBc in band spur?
Okay, so you've seen the records. Nobody has done better than minus
Minus 72. Yeah,
72.
yeah, yeah. That's true.
So, sorry, uh, sorry. We're all trying to do better. Um, can we get down to minus 100? It's still a ways off.
This is a little far. Still a little far, right? We need
It's
another
still,
breakthrough.
still, still a little far. If you think we moved from minus 70 to minus 72 in 12 years,
Yeah.
um, yeah, it's a way to go.
Okay, so he was thinking that you have maybe something cooking for that, but
We have we have an idea of how to improve the bang bang with some probability shaping, and that's one of the next things we're doing.
mhm, okay,
Will we hit minus 100? I wouldn't be promising that anytime soon.
that's a very tough number, right? That's a
Yeah.
very tough number. Okay, well, thank you very much. It's been really a great talk. Great talk. Well, I'll put on my list to recommend to my students, right? Because this is really very educative in terms of PLL design and performance. So we really appreciate your contribution. It was really a nice talk. So, would you like to do some final words, maybe?
Just again, thank you very much for the invitation. It's a pleasure. I signed up for the DL in order to be able to share what we've done with others and to get feedback. And the more questions, the better. The more I learn from these and refine what we need to do next and try to understand what other people are interested in. All the better. So thank you again for the invitation. It's been a great pleasure. Thank you.
Well, it's been a pleasure to me to host it. Uh, Ricardo was not here today, so I have the chance to be the only one. So it was really a pleasure. Thank you very much. So once more, thank you everybody for this participation and great talk indeed.
Okay. Thanks. Bye, Sandro. Bye.
Bye.